Well, hello, physics class. Welcome back after a bit of a break over the weekend. You had some time to finish up the ice lab, but we're going to get back to what we were doing before, which is the ideal gas law and heat transfer. So I've got another physical setup that we're going to use to explore these things, and that's going to be a hot air balloon. So the reason that we're going to do a hot air balloon is because it's going to let pressure, volume, and temperature interact with each other in a unique and interesting way. So just think about what a hot air balloon is. So there is a large kind of cloth balloon. It's got an opening in the top and, of course, an opening in the bottom. And suspended from the bottom by some ropes is a basket. So this is either a hot air balloon or some sort of killer plant growing out of a tiny pot. And the hot air balloon works, of course, there's I'm not going to draw it because it'll just look terrible, but there's some sort of a propane burner right there that unleashes a whole bunch of fire up here, makes this air hot, warm air expands, the density of the balloon goes down, and the balloon floats. So let's talk about how all of this works in terms of the variables in the ideal gas law. So we've got PV equals nRT. So first of all, R is a constant. There's nothing that a hot air balloon can do to change the value of R. So we don't need to worry about R being a variable here. Okay, so what things can change and what things would you not expect to change? Obviously, if there's a heat source, we're going to see the temperature change. So this can fluctuate. Now, temperature is going to be directly proportional to the things on the other side of the equation. So let's see, if the temperature goes up, will the pressure go up or will the volume go up? So this hot air balloon, as illustrated, is just what a flying hot air balloon looks like. You don't see hot air balloons expand and contract while they're flying. Now, while they're initially getting filled up, yes, but once they're off the ground, they stay the same shape, they stay the same size, so the volume's not going to change. What about the pressure? Will the pressure inside be different than the pressure outside? Now, you might be tempted to think the gas expands, so of course the pressure would be different, but that can't be. Can you think of a reason why the pressure inside the balloon has to be the same as the pressure outside the balloon? They're the same for no other reason than they're exposed to each other. There's an opening at the top, there's an opening at the bottom. If there was a higher pressure inside than outside, then the air would just immediately rush out and the pressure would be equalized. Or if there was a lower pressure inside, then the air would immediately rush in and the pressure would be equalized. So it turns out in a hot air balloon, the pressure inside and outside will stay the same at 1 atmosphere. The volume of the hot air balloon will remain the same. So the only variable left is this. What happens when the temperature goes up is, because the pressure and the volume can't change, the only thing that can happen is air will leave the balloon, and that means that the amount of air inside will go down. So we can use a hot air balloon to model a physical system in which the pressure and the volume will remain constant, and the only variables we need to worry about are the temperature T and the number of moles of air N. Okay, so how does this thing float? Well, how does anything float? In order for this balloon to float, the density of the balloon must be less than or equal to the density of the air around it. If the density of the balloon and the air are the same, it will hover. If the density of the balloon is lower, it will rise. And if the density of the balloon is higher, it will sink. So basically, what we need to do is we need to find some values for these variables such that the density of a hot air balloon is going to be equal to the density of just plain air. So let's get out of the setup of the concept and let's actually get into the setup of a problem. So I've got a hypothetical hot air balloon for you. Just imagine that the hot air balloon arrives at the field all vacuum sealed. It's not inflated or anything. So I don't know if you've ever been to a hot air balloon launching, but it all gets packed like into a van and a trailer. So let's say we got sure, that's a van, totally. And this is Hot Air Incorporated. There we go. So the doors open. Yeah, sure. And out comes a crumpled up, deflated balloon and also a basket. So this is a hot air balloon that hasn't been filled up yet. It's quite sad, actually. So how much space does it take up? And how much is it? What is its mass? So let's say that all told, this stuff has a volume of 5 cubic meters. So it would, fill up the back of that van. And let's say it has a mass of 300 kilograms. So it weighs a couple hundred pounds, takes up the back of a van. That's pretty realistic for a hot air balloon, right? I mean, I don't have a hot air balloon at home to compare it with, so go with me here. Okay, now we need to compare this with air, but we also need to fill it with air. So let's get a value for the density of air. So the symbol we use for density looks like a lowercase p. That's actually a Greek letter R. It's called a rho. So the density of air is equal to 1.225 kilograms per meters cubed. We're going to be using kilograms per meters cubed for the density and everything. So if you were to have a quantity of air that takes up the same amount of volume as this, basically fill the back of the van with air instead of with a hot air balloon. So 5 cubic meters of air has a mass of 5 times 1.225 kilograms per meters cubed, and that's actually 6.125 kilograms. So when this van is empty, there's 6.125 kilograms of air in it. However, when they shove that hot air balloon in there, there's 300 kilograms of hot air balloon in there. Okay, so now we got to inflate this balloon. So let's get this up. By the way, if you have ever seen a hot air balloon launching, then you'll know how they do this. They actually have a bunch of really big fans, like the kind of fans that you might use like on a movie set if you needed a bunch of wind. And they just like lift up one edge, stick the giant fan in it, and fill it up like it's just a big bouncy castle. It's a sight to behold. Okay, so here is our inflated hot air balloon, and now the inside of this is full of air. Let's see, how big is it? Let's say it is 1,000 cubic meters. I know that sounds huge, but 1,000 cubic meters is just 10 meters by 10 meters by 10 meters. So it's like a cube, like 31 feet on a side. That's not that big. It's probably about as big as, I don't know, 2 rooms in your house, like a bedroom and the room below it. So that's not that huge, especially not for a hot air balloon. This is a pretty small one. So how much air is that? If it's 1,000 meters cubed, okay, so density is equal to mass divided by volume. So if we're trying to get a mass like we did up here, mass is just equal to the density times the volume. So we've got density of air, 1.225 kilograms per meters cubed, times the volume, 1,000 meters cubed. So it's a lot of air. It's 1,225 kilograms of air. That is a ton of air that can fit in there. Didn't intend to rhyme, but that was fun. A ton of air can fit in here. And remember that the hot air balloon itself weighs 300 kilograms, which means this thing, okay, has a total mass of 1,525 kilograms. And it has a total volume of the 1,000 cubic meters of air plus the 5 cubic meters of stuff. So that's some excellent handwriting right there. 1,005 cubic meters. Okay, so we're going to need that for later, so let's just hold on to that. But we've got to deal with the conditions of the air. So when we're talking about the ideal gas law, one thing that we keep mentioning is STP, and that means that the air pressure is 1 atmosphere and the air temperature is 0 degrees Celsius. So one of the things about the ideal gas equation is it doesn't actually use the mass of the air. It uses the number of moles in the air. So we actually can't use 1,225 kilograms of air. We need to know how many moles that is. So if it is STP outside, that's 1 atmosphere, 0 degrees Celsius. That means, see, we've got 1,000 cubic meters of air. That is 1 million liters. If you've ever needed to use the term megaliter before, well, there's your chance. All right, so you got a megaliter of air in there, and if 1 mole is equal to 22.4 liters at STP, that just means that we need to divide 1 million liters by 22.4 liters, and we will find out how many moles that is. Turns out that a megaliter of air is going to contain 44,642.857 moles of air. So inside our hot air balloon, yes, we do contain 1,525 kilograms of air. However, more usefully, we have 44,642.857 moles of air in there. So we can actually use this and the mass to find what's called the molar mass of air. So take a second, pause the video to do this work. Could you just find the mass per mole of air? What's the mass of 1 mole of air? Pause the video, work that out, and then resume it after you've got it. Okay, so the molar mass here is going to be in the units of kilograms per mole. So we just have to do 1,225 kilograms over 44,642.857 moles, and you end up with a very small number. It's 0.0274 kilograms per mole. So we're just going to keep that. We're going to need that for later. That's going to be the molar mass of air. Okay, so now we've got two things to compare. We have an inflated hot air balloon, an inflated HAB, and an inflated hot air balloon, if you will remember, has a volume of 1,005 cubic meters, written much more neatly this time, and a mass of 1,525 kilograms. So that means that we could calculate the density of an inflated hot air balloon. It would be the mass divided by the volume. So 1525 divided by 1005 is 1.517 kilograms per meters cubed. That right there would be the density of an inflated hot air balloon. We need to make this density equal to the density of air. Clearly, the density of the hot air balloon inflated is greater than the density of the air, so it will just fall down. The only way to reduce this density is to reduce this mass, and the only way to reduce this mass is to heat up the air so that some of it will leave. So the question is going to be, how much air are we going to have to get out of that balloon in order to make it match? So here's what we're going to have to do. We need to find an expression for the density of, I keep writing a lowercase p instead of a rho. So we need to find an expression for the density of the hot air balloon. So if you'll remember, the density of the hot air balloon is made of its mass and its volume, and the mass of the hot air balloon was made of the mass of all of the stuff part of it. Let me go ahead and just do a super scientific mass of stuff plus the mass of the air. And its volume was made of the volume of all the stuff plus the volume of all the air. So the mass of all the stuff was 300 kilograms. The volume of all the stuff was only 5 kilograms. The volume of all the air is 5 meters cubed, and the volume of all the air is 1,000 meters cubed. This is the variable that we need to tweak in order to get this quantity equal to 1.225. So what is the acceptable mass of air that we can actually have in there? So here's the math on that. Actually, why don't you pause the video now, solve for that, and then resume when you're done. All right, so let's go ahead and find the mass of the air in there. That's going to be 300 plus the mass of that air over 1,005 equals 1.225. So obviously we're going to want to multiply both sides by 1005, and that means we're going to end up with 300 plus the mass of the air equals 1005 times 1.225 is equal to 1231.125. And now we just need to subtract 300. So the mass of that air is going to be 931.125. Okay, so in order for this balloon to float, I don't know how many times I'm going to have to draw a hot air balloon. If I were doing this on a board, I could just edit the drawing I had already made, but can't do that. All right, so basically, in order for this hot air balloon to float, this volume is going to be 1,000 cubic meters. Can't do anything about that. That's just the size of the balloon. However, we're only going to be able to put 931.125 kilograms of air in there. Because if we do that, then when you factor in the volume of the material of the balloon and the mass of the balloon, this is going to end up having the same density as the same volume of just air. Okay, so if we've got a inflated hot air balloon with 931.125 kilograms of air in it, it will have the same density as the same volume of air and will therefore float. Question is, we know how many kilograms of air, how many moles of air. If you will remember just a bit before, we found a molar mass for air. So if we take the number of kilograms and divide by the molar mass, we should get the number of moles. So that'll be 931.125 kilograms divided by 0.0274. 0.0274 kilograms per mole. Kilograms will cancel out. You'll be left with moles. And the number of moles here is going to be very large, 33,982.664 moles. That is a lot of moles, but remember, that same volume of air at STP contains 44,600 some moles. So from 44,000 down to 33,000, we've actually evacuated about a quarter of the air. In order for this hot air balloon to have the same density as just the air, you can only have 3/4 the amount of air in there. And the only way to get air out is to heat it up. So the question is now, at what temperature do we need to have the air inside that balloon to get enough air to leave to make the density equalize? Well, let's go ahead and do that calculation now. Remember that we're dealing with the ideal gas law. PV equals nRT. However, this part's staying the same. So the PV before is going to be the same as the PV after. But that also means that the nRT before is going to be the same as the nRT after. So I'm just going to write it like that. nRT before equals nRT after. Remember, this is based on the assumption that the PV is not changing. Okay, this is an assumption that we're making. Your equation is only as good as the assumption it's based on, and any solution that we reach is only going to be as good as that assumption. If it turns out that a hot air balloon actually flexes a little bit and the volume changes, well, then our assumption was wrong and our answer will be wrong, but only to the degree that the assumption was wrong. If it barely flexes, then our answer is barely wrong. Anyway, let's get back to this. So we've got R on both sides, so we can just cancel that out. And basically, all we've got is the number of moles before times the temperature before equals the number of moles after times the temperature after. This is the only thing we don't know. So we know how many moles were in it before. It's that large number, which I've covered up. Here we go. So, here it is. So the large number of moles we had before, 44,642.875. That's the number of moles in the balloon before it got heated up, times the temperature of the balloon before it got heated up. Remember, it was at STP, which is 0 degrees Celsius, but we have to use kelvins. So that's going to be 273 kelvins. So there's your units. That's how much air we could fit in the balloon. That's how warm the balloon was. In order to make the density the same, we need to lower the number of moles to 33,982.664. And now we just have to solve for T. So you can take a second and do that. So me giving away the answer doesn't just look like nonsense numbers I made up. But if you multiply these together and then divide by that, what you end up with is a temperature of 384.9 Kelvin. And if you want to subtract 273, you'll get 111.9 degrees Celsius. And if you want to multiply by 9/5 and then add 32, you will get 233 Fahrenheit. That's the temperature that that you need to report, though, because this is a gas equation and kelvins is the correct units for gas. Okay, so to sum up, we had a balloon with a volume of 5 cubic meters of material and a mass of 300 kilograms, clearly heavier than air. If you inflate the balloon, a whole bunch of air becomes part of the system. However, it's still denser than air because of all the material. You can lower the density of the hot air balloon by evacuating some air out of the balloon while keeping it inflated. The only way to do that is to make the air hotter. And the math happens to work out that if you heat the balloon up to this temperature, well, up to that temperature, then the number of moles inside the balloon will drop from here to here. And that will make the densities equal. Okay, so this is a long, drawn-out problem. I wouldn't want to just race through it and leave you in the dust, but all the steps should be laid out so that when I give you a similar problem, you should be able to work it out for yourself. Okay, well, make sure that you're checking the news and the links section for everything that you need. Until then, that's that.